and I'm here to tell you about an exciting time to be a neuroscientist. It's exciting both because we have a new suite of tools for measuring the brain with unprecedented precision, and also because the extraordinary recent progress in the field of artificial intelligence gives us new ways both to think about the brain and to understand our brain data. I'm going to try to introduce a few things from there today. So, but first I'm going to tell you about what it means, what we're trying to do in neuroscience. And as Tim was saying, this is a human brain. It's a large squishy ball, about 1 kilogram. But if you look down a microscope, you'll see that it's made of cells called neurons like this. About 100 billion of them, or 88 billion, I think Tim said, which are connected together by synapses in a massive network. And what we're trying to do as neuroscientists, the fundamental challenge, is to understand how do these messages sent down that network, how do they turn into your experience, your behavior, your feelings and emotions, your intelligence, how do they turn into you? That's our job. It's a fun job. If that's what your job is, then it's worth standing back a little while and saying, what does it mean to understand how something works? And I'm just going to try to introduce you to a couple of concepts that are going to be useful. First, this is the idea of abstracting something to its principles. This is illustrated here by this lovely study by Pablo Picasso, who took this very detailed picture of a bull and tried to figure out what the core principles of being a bull were. And you'll know that this is also true in the sciences. So in physics, for example, the job of physics is to reduce all of the complexities of the world down to a collection of a few simple principles. And the second idea I want to introduce to you is well summarized by this quote by Richard Feynman, who was a Nobel Prize-winning physicist. And he used to say, "What I cannot create, I do not understand." So he's saying, once I've got these principles, I need to be able to test them by proving that they can recapitulate that complexity that I saw, that I was trying to explain. And of course, these two ideas work together. Once I have better principles, I can build better explanations. And once I'm building those models that are working better, I understand more about my principles. And in understanding the brain, that's the relationship that exists between neuroscience and AI. In some sense, neuroscience is trying to figure out the principles of neural computation. How do those neurons compute? And AI is trying to use those principles to make new intelligent machines. So what does it mean to abstract the brain? Well, I've just told you that the brain is made up of a massive network of neurons. So the simplest thing we can do to make a model of the brain looks something like this. It has some hidden units in it, which are like the neurons, and it has some connection weights in it, which are like the synapses. And so since the 1930s, people have wondered if we could harness this different kind of computation to make something intelligent. And they called it a neural network. And the reason they were excited by that is because, unlike the kind of computing that most of us are more familiar with, this computer doesn't need to be programmed. Instead, it can learn from data. It can learn from its own experience. And learning is a matter of just changing these weights. It's a really easy thing for this network to do. Okay, so today I'm going to tell you how that simple idea has recently led to an extraordinary amount of exciting results. And then I'm going to show you how we can use that to think differently about the brain. And lastly, I'm going to try to give you some examples of how we can use these new intelligences as a tool for understanding our data. So let's just start by talking about the recent progress in AI, and I'm just going to summarize this very exciting period by saying we now know that simple algorithms learning from complex data can do extraordinary things. Let's start by something that we all want to do, which is to learn to make good actions. This is the field of reinforcement learning in AI, and the testbed for reinforcement learning has been games. It works something like this. This is how they train these networks. You show your neural network a situation in a game, like this position in this game of Go, and the neural network will predict or take an action on the board. It'll place a new counter in the Go. And sometime later, you'll find out if you won, and you get some reward signal. That one worked well, which is then used to go and change the weights in the network. Whoever did that, do it again next time. It was a good thing. Very, very simple idea, very, very simple algorithm. In fact, this very, very simple algorithm is borrowed from an algorithm we know about in the brain. When you guys have some orange juice or some coffee, there are some neurons in your brain in a place called the ventral tegmental area that will send that reward signal. Here's one of them firing right now when you had some orange juice. And that signal gets broadcast back to the brain and says, whatever you just did, do it again. Unfortunately, it isn't just good things. Here are those dopamine neurons again, but this time they're firing because of a nicotine infusion and a cocaine infusion. Whatever you did to get that nicotine, do it again. You can see how things like addiction can come from that. But back to AI, and that very, very simple algorithm was already doing cool things in 2012. In 2012, DeepMind made it play some Atari games, and that seems very simple, but you can see here that even that simple algorithm learned some very complicated strategies, like sending the ball over the back of the bricks so that it could kill all the bricks at once. By 2017, these systems were beating the world's best Go players. And now, in 2022, the same AI can play all sorts of games and can also control robot arms. They're trying to make this thing make general intelligence. They're also used in the real world. For example, DeepMind's our reinforcement learning algorithm are currently used in the Google data centers, where they're saving approximately 40% of energy resources. That was reinforcement learning. And the next domain I want to just quickly tell you about is language modeling, which has seen extraordinary progress. Here again, it's a very, very simple algorithm. All they have to do, it works as follows. Read some text and always try to predict the next word. I slipped because it was wet. The neural network says most likely, but maybe the neural network thinks it might be icy, or maybe with a low % chance it might be oily. And then it reads the next word, and in this case that was oily, and it says, okay, make that more likely next time. Okay, so it just has to send that back, it updates those weights, and next time it reads a sentence like that, it will think it's more likely to be oily. Again, a very simple algorithm, but if you let it read all of the text on the internet, it will do extraordinary things. So here's one of the extraordinary things that I asked it to do. This is a system called ChatGPT, which anybody can access. I'm sure many of you have played with it, and if you haven't, you should. It's really fun. I asked it to write me a rap battle about neurogazer, and it wrote this. I'm the neurogazer, the brain's prober. I see what you're thinking, no need to decode ya. I scan through your neurons, your synapses and cells. I'll find what you're hiding, no secrets to tell. It knows about rhyming, it knows about verses. It has these abstract concepts, all from just trying to predict the next word. Amazing. It's also useful. Here's something else I asked it to do. Can you write me some code to build a hidden Markov model? Now, that's something that only geeks like me understand. That's kind of my job, writing this kind of stuff. now you don't need me. You can get ChatGPT. Anybody can write code that I would normally write. You can tie these language models to image models as well. And now we can ask neural networks to show us pictures of things that we might never see in the real world. Can you show me a picture of a brain scanner in the style of Van Gogh? I think this is a lovely image maybe NeuroGazer may want to use. Or a photo of a cat and a mouse playing chess. So suddenly, over the last 10 years or so, people are making these neural network models work and do things that we could never have imagined. So maybe we can use them to try to understand how intelligence is working in the brain. And so this section of the talk I'm going to summarize by saying something like, neuroscience is interested in reducing things to computational principles. But with AI, we can see what those principles look like when they're confronted with the data of the world. And so we can see what they should look like in our neurons. Let me just give you one example of this, and I'm going to take you back to this idea of intelligence as abstraction. I'm going to show you an example where that's true in your own brain, where there are cells that are really showing this abstraction in your brain. And so let me just give you this simple example. Imagine you're a mouse looking for this cheese, having run down this tortuous path. Then the next time you want some cheese, if all you're doing is repeating good actions, then you have to take the same tortuous path again. But if you're able to build an abstraction, if you're able to understand how two-dimensional space works, for example, you have an abstract concept of what it is to live in two-dimensional space, then you can draw a vector and you can find a shorter route to the cheese. Humans also can do this. In fact, interestingly, this ability varies across humans and also across cultures. I'm just showing this slide. This is a lovely study from my friend Hugo Spears. I'm showing it because although the best people in the world at this navigation ability are Finnish, both the British and the Koreans are really right next to each other, in this ability. But back to the brain. The reason you can do this is because of some cells in your brain. Here again is a rat. And what I'm showing you is two types of cell and when they send those messages. The cell in the middle is a place cell. It sends a message whenever the rat is in a particular place. For the purposes of today, it's a boring cell. But the cell on the right is amazing because it fires in lots and lots of places, and those places lie on a perfect grid. So whenever it passes any of those points on a grid, it sends a message saying, I'm on this grid. So that cell is an abstraction of 2D space, just like grid lines are on a piece of graph paper. But it's amazing, that's a single cell in your brain firing out the coordinates in a graph. So how can AI help us understand this? Well, remember what I told you about language models. They just try to predict the next thing in a sequence. I slipped because it was oily or wet. Well, let's think of another type of sequence you might see. A whole bunch of things you might see in a whole bunch of actions. You might see a light bulb, go right, a broomstick, go down, a motorbike, go right. And then you could ask, can I predict what's coming next? And the answer is no, nobody in here could predict what's coming next unless they knew that those different objects were arranged in space and they were able to remove all those objects and build this abstract understanding of space. Then, of course, you can tie the new objects onto this abstraction and you can then predict the next thing. And so if we train an AI just to predict the next thing, then it's going to have to learn the abstraction or else it can't do it. So let's try and do that. And if we do that, and then we look inside the AI, now we see grid cells exactly like the brain. And this tells us something deeper. These grid cells are doing something deeper. They're not just coding for space. They're understanding the abstract nature of these sequences, so we should be able to see them in situations that are not spatial. And indeed we can. We can go back into the brain and look. And now these grid cells are there, but they're not coding for physical space. They're coding for spaces in concepts in your mind. These grid cells are now coding in the spaces of birds. Imagine a two-dimensional space where one axis is the length of the neck of a bird, for example, and another axis is the length of the legs. And grid cells are spanning this conceptual space. And this has now been shown in many different conceptual spaces that are a long way away from physical space, but share the same structural properties. Furthermore, the notion of two dimensions, that structural property, is only one of many structural properties that sequences could have. And so this is finding parallels between these cells here, grid cells, and these other beautiful cells, for example, which learn to count this as it's increasing, as a mouse does more and more laps of a maze. So those two phenomena are really the same thing. Now, grid cells are one of the first cells to be affected in Alzheimer's disease. And it's true that people with Alzheimer's disease do have problems with space. For example, they might not remember where they've put their car keys. But they also have non-spatial problems. So for example, this process of doing the dishes is also a structured sequence, right? So you load the dishwasher, then you let it run, then you put all the dishes away. My gran had Alzheimer's disease, and she would often do something which I found very strange at the time. She would often load the dishwasher and then put the dishes away without ever turning the dishwasher on. She didn't understand the abstract structure of these sequences, having lost that same region of the brain that has grid cells in it. So here AI has made a really deep link between two different things that are affected in a disease. So I just told you one example, it's one close to my heart, but this has been happening throughout of neuroscience recently. Here are three of many others, situations where trained deep neural networks have been able to predict the brain activity in different parts of the brain, the language system, the visual system, hearing system, for example. Okay, in the last part of my talk, I wanted to introduce the idea that AI might be used as a tool for neuroscience. And I want to summarize this section by saying we're beginning to be able to see what the neurons are saying to each other in a way that we never have before. And so in order to understand what I'm going to show you now, you have to realize that a neural network represents information as a pattern of activity. And so this pattern of activity here, you can see on the left, might mean a lion. Whereas this pattern of activity here underneath might mean a penguin. So those patterns of activity, once we know those patterns of activity in the network, we can link them to other things. For example, here, somebody is linking different patterns of activity to language, to words. And so you can look once you've done that, you can ask the neural network, tell me what shock looks like. Or tell me what Africa looks like. And it produces an image like this. Tell me what winter looks like, or Roman. It's starting to show you what concepts look like. But imagine instead of tying those patterns of activity to words, instead of doing that, if we tied them to patterns of brain activity, now we could take a pattern of brain activity and say, what does that look like? We can really almost see what the neurons are saying. So let's see how this would work. Now we can take the same pattern of activity and try to learn or understand the relationship between the pattern of activity in the brain and the pattern of activity in the network, and then produce an image. And this is really working amazingly well now. Here's, I think, the state-of-the-art, most recent example, where the top row, there's a person lying in an MRI scanner, just like the one in NeuroGazer, and the top row is an image that a person is actually looking at. And the bottom row is an AI that can only see the person's brain activity, guessing what the person is looking at. And look how amazingly similar it is. We have a giraffe, whatever this strange insect is, a fire engine. We can really see with some incredible detail from the brain activity what's inside the person's thoughts. It's working pretty well for language, for vision, and amazingly to me, it almost works for language as well. Look at this. This is now somebody listening to a story with complex, deep emotions and thoughts in it, and then an AI looking at their brain activity in these brain regions here and guessing what those thoughts and emotions were. And so this one is not quite as impressive in terms of its ability, but it's much more impressive in terms of what it's trying to do because of how complex the ideas are. And so it almost does it. So this is what the person listened to. I didn't know whether to scream, cry, or run away. Instead, I said, leave me alone. I don't need your help. Adam disappeared, and I cleaned up alone crying. And the neural network looks at the brain activity in these brain areas, and it reads out the following. Started to scream and cry. Look, it's exactly the same. And then she just said, I told you to leave me alone. You can't hurt me, I'm sorry. And then he stormed off. Adam disappeared. I thought he'd left. I started to cry. I mean, it's really almost there. We can almost read out the people's deep internal emotional thoughts. This last example is one that's close to my heart. Maybe you, like me, think you spend a lot of time doing nothing, wasting a lot of time sitting on a sofa, drinking a cup of tea. Well, I've got really good news for you. That time is not wasted. The brain uses that time to reorganize its experiences into new knowledge. Let me try to show you how. And to explain how, I have to tell you about this extraordinary phenomenon called replay. It's an amazing phenomenon. To understand this graph, this is a rat. So this replay was first discovered in rats. This is a rat that's running along a track. And underneath here, I'm plotting what its brain activity, where its brain activity thinks it is on this track. So let me just give you this example. So its brain activity is resting, the rat's resting now, and the brain activity says it's in the same place. And then the rat's running, and the brain activity moves, realize it's moving, then resting, and now it's running again. And you might think, and you'd be right, that is not particularly impressive. If you want to see where the rat is, you don't need its brain activity, you can just look at it. But look at what happens here. This is amazing. In these rest periods here, when the animal's resting, there are these tiny blips of activity. And if you zoom in, you can see that the animal is not running up and down the track, it's resting, but its brain is running up and down the track at hundreds of times the speed. Rapid, quick replay, trying to remember what it's been doing or predict what it's going to do in the future. So recently, we've shown using AI that you can measure those same replay events in humans. And we've shown that it doesn't just repeat your exact experience. Instead, it reorganizes knowledge to make sense of events. So just to give you an example, imagine you were on your way home tonight and you heard an ambulance. And then you saw this crashed car. And then you saw a sign saying there was an icy road. Then later on tonight, when you were resting, your brain will replay something different. It's going to replay a car crash, a crashed car, the ambulance coming, but it's replaying it in the correct order. It's figuring out what happened to play out these events, making new inferences, updating your knowledge. We've also shown that not only does that happen when you're resting, but it's also an integral part of understanding your ongoing experience. Something that's always amazed me is that humans can understand a film even if it's played in totally the wrong order. Anyone that's seen the film Pulp Fiction or Memento will know that that's the case. So let's try that here. Here's a film of somebody making a cup of coffee, a very boring thing, but it's played in entirely the wrong order. As you watch this, you're going to be able to realize which things are in the right and the wrong order and stitch them back in the right place. What was happening in your brain right then was that as you saw the different parts of the movie, your sensory processes were processing what was going on. But each time there was a pause and a flip between scenes, little replay events were happening. They were stitching things back together in the correct order. And we can now measure those in humans for the first time. So I just wanted to end up by saying that I think it's really an extraordinary time for neuroscience in terms of the opportunities, what we can measure, and the kinds of ideas that we can investigate. And I think it's like totally exciting that something like NeuroGazer can bring that to society and do it at scale in a way that is likely to really make the most of these cool ideas in the future. So thanks very much, and I'm excited to be here.